This is a presentation for Generations, a MATLAB project by Joshua R. Campbell, created for ABE 205 for spring 2013. My project is called Generations. At the command line, typing in Generations 2 starts the program. The first input is the target population size. And for purposes of this demonstration, I use the current population of the Earth, which is approximately 7 billion. The average reproductive age is the age I'm using to represent when all the offspring of a generation are produced, and it also determines the time step between generations. The reproductive rate, offspring per individual, is the number of children that come from each individual. So each pairing would produce twice that rate. So in this example, I'm using 2, which means a couple would produce 4 offspring. Childhood morbidity is the number of or the percentage of children who die off before reaching the reproductive age. For a conservative figure, I'm using 10% for this example. And then average lifespan is the number of years between birth and death. And by dividing the lifespan by the reproductive age, we can determine how many generations a person actually lives, which will become important for the iteration. And then that's the last variable, and boom, you get the output. So 7 billion people could descend from one couple within 652 years, assuming there's an external population to provide or to absorb inbreeding pressure. In addition to the output number, there's also a graph with 2 lines. The stepwise model computes it by generation, so a time step with a time step equal to the reproductive age. An exponential model was derived based on the output of the stepwise model using a standard y equals CE to the KT model. So let's take a look under the hood. The basic code is clearing all the variables so you can have a fresh start each time you run it. Modern pop is the target population, and F1 is the incrementing variable to be used in the loop, and pop initial is the starting population of 2 individuals. And here we have our 3 population components: breeders, non-breeders, and deaths. In any given generation, the number of breeders is equal to the surviving offspring from the previous generation, and each time that's calculated, it's stored in an array. Non-breeders are individuals who have survived past a single generation, who have already reproduced, but have not died yet, so they're not adding or subtracting from the population. And then deaths is the deaths at a given generation is equal to the number of non-breeders who have reached the end of their lifespan. So depending on what the generational lifespan is for the model, the deaths will equal the number of breeders after so many generations, usually 3 or 4. So those 3 factors are summed. The first 2 are summed, and then deaths are subtracted to get the population sum at each generation step. And then we have the inputs for the variables for reproductive age, reproductive rate, morbidity, and lifespan. And then, as I mentioned before, the generational lifespan is the lifespan divided by generation time. And here's the first half of the iterative loop. So while the sum of the population sum array is less than the target population, the loop increments, calculates the number of breeders in each generation, and then adds that number to the array. If it's found that morbidity is too high or reproductive rate is too low, the population is called non-viable, and it breaks the loop. So it doesn't just try to keep calculating a non-growing population forever. And then non-breeders for a population are equal to the breeders of the previous generation, and that's stored in another loop. If in the first couple of generations of the model, while the non-breeders have not reached the end of their lifespan, there will be no deaths outside of childhood morbidity, which isn't included in the number of deaths. So I have an if loop that delays the calculation of deaths until the till the first generation reaches the end of their lifespan, at which point they're counted into the number of deaths and added to the death array. So the total population is summed on each generation, adding breeders to non-breeders and then subtracting the number of deaths, and that's added to another array. The number of years that have passed since the beginning of the simulation is calculated with the incrementer times the generation time, and then that number is stored into an array so it can be used for graphing. And then after that while loop is done, there's an if loop that checks the viability of the population. If the population was found to be inviable, then it gives an error warning that it was a null simulation. If the population was found viable, it spits the variables into the function to determine the exponential simulation for the model. And here we have the function which I called Sirius, which takes in the maximum time, max and min time, max and min population, and the target population, and outputs the actual time it takes to get to the target population in modern pop time. The time span is a incremented timeline by single years, and then the single year timeline is fed into pop steps to get the exponential population for each year of the model. It kicks back to the positive viability loop and graphs the exponential model against the stepwise model with a small dot showing where the stepwise model reaches the target population. And that's it. Too easy. Thank you.